In this lesson, we're going to teach about head and energy and kinetic and potential and energy grade. Right now, we're filling up this tank with fluid from our pump. And our pump endows energy by accelerating the water. It does this by a vane that's curved, and as it turns, actually turns backwards like a highlight, and it slings the water. As it slings the water, it accelerates it. And acceleration times mass equals force, so the pump endows force onto the water. This force is what forces the water to rise to a height. By generating force, we can force the water to accelerate upward. We're actually always accelerating the water upward into a column of water with the pump. That's its whole purpose. As we fill up this tank, we'll notice that this height right here is increasing. That's because we're adding potential energy. I'm increasing the height a little higher. We're doing it rapidly now. Increasing the height very quickly. Watch the columns of water in the tubes, and you'll see how they rise with potential. That's because we're building up more force, and it's storing more energy. Okay, I'm back. Okay, so we've increased our height, which increased our energy storage. And by increasing the height, we've actually increased the weight of the water in here. Of course, weight is force. And force divided by area is pressure. And this is what people like to talk about, pressure, but I want to get away from pressure and talk about head instead of pressure. By adding this weight and this force, we've taken the force, divided it by the mass, and we have acceleration. So this head of water is actually accelerating the water out of the tank and through the piping system. This piping system is just like an electrical circuit. These are resistors. The valve's a resistor, the 90s are a resistor, the pipe is a resistor, this 90s a resistor, and behind here, I actually have a little orifice. It's a small washer, and it has a hole in it, and this resistance acts like a long piece of pipe. That's why the water stands up here instead of being at zero going out, because we know at the end of our run we have no energy left. We've used all of our energy, going from maximum energy to zero energy. And just like in voltage, we can actually measure the energy dropped across the line. Just like you have a resistor and use watts to size your resistor, that's because it's dissipating energy in heat and vibration. This dissipates heat and energy and vibration. So we take this potential and we start doing work. Potential is the ability to do work. We start doing work, and so this forces the water to accelerate through the pipe. Mass times acceleration equals force. And we get a voltage drop or a pressure drop across each one of these sections of fittings and pipe because of resistors. Just like you measure a voltage drop across a resistor, we measure a potential. The potential in head is the same as the potential in voltage. It can be thought of the same thing, and we can see a difference of pressure across here, or a difference of head and potential energy. So we have a difference of potential energy. Now we want to talk about our head not as pressure, but in instrumentation we want to talk about head in feet and inches and millimeters and meters, because this height can be translated to PSI. We know that this is weight over an area, and weight divided by area, or force divided by area, is pressure. Therefore, pressure is pounds per square inch, PSI. So we got to understand this is weight, and this weight is the force which is doing the work. And we can calculate how much work it's doing by the pounds per square inch. So 27.7 inches of water equals 1 pound of water per square inch. If I took a 1 inch square column and I took it one by one, I raised it 27 inches high, 27.7 inches high, it would actually weigh 1 pound of force or weight. So that's how we can translate our height into PSI. So this difference in height is our velocity. Now we fall, and our velocity equals the square root of 2gh. So this differential height is proportional to the velocity of the water flowing. The velocity times the area equals our volume. So by putting an orifice which has a precisionally drilled hole, we have an exact resistor here. This acts just like an electrical resistor, a precision resistor. And so we can measure the potential of energy across it, same as voltage. By measuring this difference of potential, we can tell how fast the water is flowing, and just like you have a voltage meter and you have a resistor, you can tell what the current flow is. We can tell what the water flow is. So our potential, you see we're up here, you would think it would squirt out, only if you block off the end. So as the height gets higher, the faster it flows, the more potential we have, and the more the kinetic energy is required to drop it. So when you have more potential to provide more kinetic energy and a higher force, it's a higher differential force, so it causes it to accelerate through the pipe faster. Okay, if I would put my finger behind this and block off this orifice a little bit, I'll deaccelerate this. This is the same principle as a control valve. And when we deaccelerate it, the potential energy will increase. So watch the potential energy increase. As I slow it down, potential energy increases. And well, we're real slow, so these are almost exactly even. There's only a 1/4 inch difference. They're almost even because it's almost to a standstill. Notice your height is increasing a little bit. It's increasing a little bit. It's increasing a little bit. It's increasing a little bit. Now I'll move my finger away from it. We'll see the potential energy change to kinetic. It starts accelerating faster, and the tank will start falling. And it slowly falls down. So this can be understood as resistors, and this valve and these 90s are a resistor, and this orifice is a resistor, and this piece of pipe is a resistor, and this orifice back here is a resistor. And we take the potential energy, it's the difference of potential, just like voltage, and so we can see our potential is the ability to do work. Okay, one last thing is we're going to talk about the difference of pressure and head. When we're talking about piping systems, we're putting a gauge on it. The gauge will be in PSI, pounds per square inch. That's because it doesn't matter if it's water or gas or alcohol or oil. It's just molecules impinging in the side of the pipe, and it is bouncing on the side of the pipes. And as these molecules imping the side, they're actually pounding on it like a hammer, and this generates a force, and force divided by area is pounds per square inch. And this pounds per square inch will tell us when the pipe's going to rupture or when the gasket is going to rupture. So it's easy to talk about PSI, so our gauges will typically be in PSI and not feet. When we talk about feet, we'll use the feet to measure the height in the tank. So we'll take the pressure, convert it to feet, because that's exactly what we want to measure, is how much feet of water we have. It's potential energy. Now when we're sizing our orifices and our valves, again, we're talking about feet or inches of water. On an orifice, we typically talk about the formula in inches of water. And in a valve, we'll talk about PSI because it's a convenient unit for the piping system. The piping system is designed in PSI, so we'll size our valve in PSI because typically it's 15 to 40% of the pressure drop across the pipe. We take that and add 40%, 15 to 40% across our valve to make it function above and beyond the piping system. And again, we'll take the square root of the orifice and the square root in the valve. We take the square root because velocity equals square root of 2gh. And of course, we're looking at the difference of height, the difference of force, so it causes it to accelerate. And we translate this square root of 2g, 2 times acceleration of gravity, into our coefficient for the valve or the orifice. Pumps are sized in feet of head times pounds or foot-pounds of work. We have orifices to measure our flow, and we have valves, which are variable orifices, that control our flow. And these are based on the weight of the fluid. Our weight of the fluid equals our density compared to the density of water. And this is a ratio. So it's either heavier than water or lighter than water, and this is based on weight. And this weight, as you saw, is proportional to the height of the column. So the height of the column times the specific gravity equals the height of if it was water. In other words, if it's an alcohol and it's 0.78, it'd only be 78% of the height if it were water. So remember, specific gravity is the weight per volume of a liquid over the weight per volume of water. And with gases, it's the gas or vapor weight per volume over air weight per volume. And these have to be referenced to standard references so everybody has the same reference. So water and gas will typically be 60 degrees Fahrenheit and 14.7 psia. So make sure that it's 60 or 68 degrees or whatever reference you're using. There's multiple references out there for standards. Okay, that's it. We're done. We're out of here. Thanks for hanging in there. Bye.